Today we're going to prove three theorems which are collectively known as homomorphism theorems. A homomorphism is a mapping between two algebraic objects that preserves their algebraic structure. A homomorphism between two vector spaces is just a linear transformation between these spaces. But we will also consider homomorphisms of other algebraic objects. So, for example, homomorphisms of groups. And these theorems that we're going to discuss today will have analogs for other algebraic objects as well. We begin with the first homomorphism theorem, which says the following. So let T be a linear transformation from vector space V into vector space W. Then the quotient of a vector space V by the kernel of this linear transformation is isomorphic to the image of the transformation T. So here, image of T is a subspace in the vector space W, and what we're claiming is that the vector space, which is the quotient of V by the subspace, which is the kernel of T, is isomorphic to the image of T. Let us give a proof of this theorem. We need to construct an isomorphism between these two vector spaces, the quotient of V by the kernel of T and the image of T. We will call this isomorphism T bar. So this will be a linear transformation from the space V quotient by kernel of T to the image of T. The elements of the quotient space are equivalence classes. So we define T bar of an equivalence class of a vector V as T of V. So here the domain of T bar is the quotient space V quotient by the kernel of T, and we can see that the values of T bar are assumed in the image of T, because this is T of some vector V. So what do we need to prove? Well, of course, we need to prove that T bar is an isomorphism. But this is actually going to be the second order of business. And the first order of business is to show that it's well defined. The thing is that T bar is defined on equivalence classes. And whenever we work with equivalence classes, we need to make sure that our constructions are well defined. So what does it mean to be well defined in this particular situation? So here we define the right-hand side using vector V. But in the left-hand side, we have an equivalence class of V. And vector V is just one representative in this equivalence class. So what we need to show is that if we take two different representatives of the same equivalence class, so if the equivalence class of V1 is equal to equivalence class of V2, then we need to show that the right-hand side does not depend on the choice of a representative in this equivalence class. So we need to show that T of V1 will be equal to T of V2. So this is what it means for T bar is well defined. So what does it mean that these two equivalence classes coincide? Well, this means that these two vectors are equivalent to each other with respect to our equivalence relation. And this says that the difference between these two vectors, v1 minus v2, belongs to our subspace that we quotient out. In this case, this is kernel of T. But this says that if a vector belongs to the kernel of T, this means that T applied to this vector is equal to 0, because this is the definition of the kernel. And then, since T is linear, so this says that T of v1 minus T of v2 is equal to a 0 vector. And this gives us exactly what we need. T of v1 is equal to T of v2. And this tells us that the linear transformation T bar is indeed well defined. The right-hand side of the definition of T bar does not depend on the choice of the representative in the equivalence class. Now, to prove the second part, so that T bar is an isomorphism, so here this entails two things. That A, T bar is linear, and B, that T bar is injective and surjective. So that is, it is a one-to-one correspondence. Let us show that T bar is linear. For this, we need to show that T bar of the sum v1 plus v2 is equal to T bar of v1 plus T bar of v2. And the second property is that T bar of C times v is equal to C times T bar of v. Let us look at the first equality. So let us take the left-hand side. We have T bar of v1 plus v2. Now we add equivalence classes by taking the sum of the representatives and taking the equivalence class of the result. So this is T bar of the class v1 plus v2. And by our definition of T bar of an equivalence class is T applied to the representative of this equivalence class. So this is going to be T of v1 plus v2. And if we take the right-hand side, so here we have T bar of the class of v1 plus T bar of the class of v2. Again, by definition of T bar, so this is equal to T of v1 plus T of v2. And we see that left-hand side is equal to the right-hand side, since T is a linear transformation. So here we get that T of v1 plus v2 is equal to T of v1 plus T of v2. And I leave verification of the second property of linearity for T bar as an exercise for you. Now we need to prove that T bar is surjective and injective. So let us look at surjectivity. Let W be an arbitrary vector in the image of T. So then, because it belongs to the image, we know that there exists a vector V in the space V such that W is equal to T of V. But we know that T of V is equal to T bar of the class of V. So we see from here that W belongs to the image of T bar. And this tells us that T bar is surjective. And let us prove injectivity of T bar. Suppose some class of V belongs to the kernel of T bar. So this is equivalent to saying that T bar of this class is equal to 0. But what is our definition of T bar of a class? T bar of a class of V is equal to T of V. So this is equivalent to saying that T of V is equal to 0 vector. So which is equivalent to saying that V belongs to the kernel of T, and the kernel of T is precisely the subspace that we quotient out. So this means that the fact that V belongs to this subspace is equivalent to saying that the class of V is equal to 0 class. And the conclusion of this is that the kernel of T bar consists of just a 0 class. And this tells us that T bar is injective. So we proved that T bar is well defined, it's linear, and it's injective and surjective. Thus, it's an isomorphism, and this tells us that these two vector spaces, the quotient of V by the kernel of T and the image of T, these two vector spaces are isomorphic. In finite dimensional setting, we know that two vector spaces are isomorphic whenever their dimensions are equal. So we see that the first homomorphism theorem in this setting is compatible with our rank nullity formula. So if we look at dimension of the left-hand side and the right-hand side, then we get the equality that the dimension of the quotient space is the difference of the dimension of the space minus the dimension of subspace. So on the left, dimension is dim V minus dimension of the kernel of T. And on the right-hand side, this is equal to dimension of the image of T. And this is the formula that says that the dimension of the image of T plus dimension of the kernel of T is equal to the dimension of the domain. Or in the language of matrices, so this says that the rank of a matrix plus the nullity of the matrix is equal to its number of columns. It is important to point out that the first homomorphism theorem is used not in the way how it is stated. In the statement of the first homomorphism theorem, we are already given a linear transformation T from V to W. But in fact, most of the time that we use this theorem, this linear transformation T will not be given and would need to be constructed. To illustrate this, let's consider the following example. Let U be the following subspace in the space of polynomials with real coefficients. So U consists of all polynomials P in R of X such that P evaluated at point 2 is equal to 0. It's easy to prove that U, in fact, is a subspace. And so what we want to do is we want to show that the quotient of R of X by the subspace U is isomorphic to R, or that is one-dimensional vector space over real numbers. This is a very typical example of applications of the first homomorphism theorem. So what we want to do is we want to identify a quotient space. So here, this quotient space is given in a rather abstract way. So we have an infinite dimensional vector space, and we take a quotient by its infinite dimensional subspace. And what we want to prove is that this complicated quotient has a very simple realization, as a one-dimensional vector space over real numbers. This is the primary purpose of the first homomorphism theorem. By applying it, we want to identify quotient spaces with some very concrete realizations. The challenge here is that in this problem, we have something that looks like a conclusion of the first homomorphism theorem, but there is absolutely no linear transformation T here. And this is what we need to do. So we want to construct the linear transformation T. In order to do this, we need to match the pieces that were given here with the pieces that appear in the first homomorphism theorem. So the first homomorphism theorem says that V quotient by the kernel of T is isomorphic to the image of T. If we want to apply the first homomorphism theorem, then we need to align all these pieces of the puzzle. So this tells us that we need to take V as the space of polynomials. As image of T, we should take the real numbers. This already suggests what kind of transformation is T. So the domain of T must be the space of polynomials, R of x, and the image of T must be real numbers. So we want to construct a linear transformation from the space of polynomials into real numbers, and the kernel of this transformation T must be our space U. So this must be the set of polynomials P such that P evaluated at 2 is equal to 0. This transformation must turn polynomials that have 0 value at 2 into 0 numbers. So now we have to be clever, and we need to cook up a linear transformation with a prescribed kernel. So what should be T of a polynomial P of x? So the result should be a number, and our construction of T must have this prescribed kernel. The right way of doing this is to say that this transformation T converts a polynomial P of x into its value at a point 2. So we see that the result will be indeed a real number. And what will be the kernel of transformation T? The kernel of the transformation T will be precisely polynomials with the property that P of 2 is equal to 0. So this means that the kernel of T is precisely our subspace U. And then applying the first homomorphism theorem, so by first homomorphism theorem applied to this linear transformation that we have just constructed, we obtain that the space of polynomials quotient by the kernel of T, which is U, is isomorphic to the image of T, which is real numbers. And it's clear that this constructed transformation is surjective because it transforms a constant polynomial C into the same constant value. So any real number can be obtained as a value of linear transformation T. So recapping this example is that we use first homomorphism theorem to find explicit realizations to abstract quotient spaces, and we do this by constructing linear transformations that we will have required properties. Now let us discuss the second homomorphism theorem. So we state the second homomorphism theorem. Let T be a linear transformation from V to W. And let U be a subspace in kernel of T. Then T factors through the space V quotient by U. So what it means is that we have the following diagram. So we have V, and T sends V to W. And we also have the space V quotient by U. And here we have the map, which is our canonical projection. And the claim of this theorem is that there exists a linear map T bar. And so this dashed bar on the diagram means the claim of existence of such a homomorphism. We claim that a linear transformation T factors through the space V quotient by U. So this means that there exists a linear transformation T bar from V quotient by U to W such that linear transformation T can be written as a composition of the canonical projection P followed by T bar. The existence of a linear transformation from this quotient space with this property is the claim of the second homomorphism theorem. And again, we point out that the second homomorphism theorem is used not in the way how it is stated. And the real application of the second homomorphism theorem is the following, that second homomorphism theorem is used to define linear transformations with quotient spaces as domains. So if we need to construct a linear transformation T bar from some quotient space V quotient by U to another vector space W, the way how it's done is you first construct a linear transformation T from V to W with the property that the subspace that you want is sitting inside the kernel of the transformation T that you need to construct. And once you do this, then applying the second homomorphism theorem, you obtain a linear transformation T bar from this quotient space. Now let us recall what was our canonical projection. So the canonical projection P was a transformation from V to the quotient space V quotient by U that sends each vector to its equivalence class. So this formula, T is equal to the composition of T bar with P, is equivalent to the following. It says that T of a vector V is equal to T bar of P of V, but P of V is the class of V. And so this becomes T bar of the class of V. And this formula tells us how we should define T bar. So because now there is only one way how T bar could possibly work. So we set T bar on equivalence class to be T of V. This is the only possible construction of T bar which will be compatible with this composition formula. Now we need to see that this formula works, so that this formula indeed defines a linear transformation. We need to show that the map T bar from V quotient by U to W given by the formula T bar of a class of V is equal to T of V is, first of all, is well defined, and secondly is linear. And remember, whenever we operate with equivalence classes, we always need to worry about that our constructions must be well defined. Now, what does it mean that T bar is well defined? We need to show that the right-hand side of this definition of T bar is independent on the choice of a representative class. So this means that if we have the same equivalence class given by two different representatives, so if the class of V1 is equal to the class of V2, we need to show that the values of the right-hand side will be the same, so that T of V1 will be equal to T of V2. And indeed, so if the classes of V1 and V2 are the same, so this is saying that the difference between V1 and V2 belongs to the subspace that we quotient out, so that is U. But we are given that U is a subspace inside the kernel of T. And so this will tell us that T of V1 minus V2 is equal to a zero vector, and this implies exactly what we need. So if we apply linearity of T, then we get T of V1 is equal to T of V2. And now, to show that T bar is linear, we need to show that A, T bar of the class of V1 plus the class of V2 is equal to T bar of V1 plus T bar of V2, and B, that T bar of a constant times the class of V is equal to constant times T bar of the class of V. For the first property, the left-hand side is equal to T bar of the class of V1 plus V2, and by definition of T bar, right here, so this is T of V1 plus V2. And the right-hand side becomes, by the same definition, it becomes T of V1 plus T of V2. And we have equality since T is linear. And the second property of linearity, as usual, I'll leave to you as an exercise. And finally, the factorization claim that T is equal to the composition of canonical projection with T bar will hold because of our construction of T bar. So here we already checked that T bar of P of V, so is equal to T bar of the class of V, which is by our construction of T bar, this is T of V. And we see that the composition of the two maps in the right-hand side is equal to a linear transformation T. Before we discuss the third homomorphism theorem, let us look at the following situation. So suppose T is a linear operator from vector space V to itself with an invariant subspace U. So this means that T applied to this subspace will have results in the subspace U. Now we know that if we choose a basis of V that starts with the basis of the subspace U, then the matrix of this transformation will have the form with a block of zeros. So here we will have a square block of size k, where k is the dimension of U, and we will have a block of zero underneath, because this linear transformation will send any basis vector from the subspace U to a subspace U. So this means that in images of these vectors, only the first k basis vectors will appear. This invariance tells us that we can restrict T to the subspace U, and then this will become a linear operator on the subspace U. And the matrix of this restriction will be written here. So this k by k block is the matrix of the restriction of the operator T to the invariant subspace U. Now, the question that we want to ask, well, we understand this block, but how about the other square block? What is the meaning of this square block in the opposite corner? The answer to this question is given by the third homomorphism theorem. So we have the following third homomorphism theorem. Let T from V to V be a linear operator, and we recall that operator is the case of a linear transformation with the target space equal to its domain. And let U be a subspace in V invariant under T. So this means that T applied to any vector in U has a result in U. Then there exists a linear operator T hat from V quotient by U to V quotient by U such that the following diagram commutes. So here we have the following diagram. So we have vector space V, another copy of vector space V, and the operator T acting between these two vector spaces. Then downstairs we have the quotient vector spaces V quotient by U and V quotient by U. And we claim that there exists a linear operator T hat that acts between these two vector spaces. And vertically we have canonical projection. So we have canonical projection from V to V quotient by U and the same canonical projection here. So we get a square with 4 maps on this diagram. And the claim that this diagram commutes means that if we travel in this diagram following the arrows, then the result does not depend on our path. So this tells us that if we follow these two arrows, so this will give us composition of P with T is the same as if we follow these two arrows. So here we'll have P followed by T hat. So here we are given a linear operator T from V to V, and since we have these quotient spaces, we also have the canonical projections, and the claim is that there exists a linear operator on the quotient space downstairs from V quotient by U to itself, such that this diagram commutes. So this means that these two compositions produce the same linear transformation. And to answer the question that we posed, this lower right corner is the matrix of the operator T hat on this quotient space. Let us analyze this equality of these two compositions. So this says that for every vector V in the vector space V, we will have T hat composed with P applied to vector V is equal to P composed with T applied to vector V. Or on the left, we have T hat of, so the canonical projection applied to vector V gives us an equivalence class of V. And on the right, we have canonical projection applied to T of V. So this will be the class of T of V. And what we see is that this gives us the only possible definition of the operator T hat acting on the quotient space V quotient by U. So following this rule, we set T hat of the class of V to be the class of T of V. And we want this to give a linear operator from V quotient by U to V quotient by U. So here we need to show, first of all, that T hat is well defined. Again, we need to do this because the definition of t hat is given in terms of representatives of an equivalence class. And secondly, we need to show that t hat is linear. So what does it mean to show that t hat is well defined? So if we have the same equivalence class given by two different representatives, we need to show that the right-hand side of the definition of t hat will not depend on the choice of a representative. So we need to show that the class of t of v1 is equal to the class of t of v2. Now let us show this property. Suppose the class of v1 is equal to the class of v2. So what does it mean? So this means that the difference between these two vectors, v1 minus v2, belongs to the subspace that we quotient out. So this belongs to U. But then let's apply t to this vector. So this will tell us that t of v1 minus v2 also belongs to the subspace U, since U is t invariant. And so if we take a vector in U and apply transformation t, then the result is again in U. And this tells us that the class of the vector t of v1 minus v2 is the zero class, because the class of any vector in U is a zero class in the quotient space. And then, since t is linear, we get that the class of t of v1 minus t of v2 is the zero class. And from here, we conclude that the class of t of v1 is equal to the class of t of v2. And here we use the fact that in the quotient space, the class of a difference is equal to the difference of the classes of the two vectors. And that's exactly what we wanted to prove. So we assumed that the classes of v1 and v2 are the same, and we proved that the classes of t of v1 and t of v2 are also the same, which means that t hat is well defined. Now, as an exercise, I leave it up to you to prove that t hat is linear. So recapping, the third homomorphism theorem tells us that if we have a linear operator on a vector space V with the invariant subspace U, then we obtain a linear operator on the quotient space. The way how the third homomorphism theorem is applied is that when we need to construct a linear operator on the quotient space, V quotient by U, then we do it by constructing an operator on the vector space V upstairs such that it has the property that it will have U as an invariant subspace. Let us establish two more results as applications of our homomorphism theorems. These results are sometimes called isomorphism theorems. So here we have the first theorem. Let U and W be two subspaces in the vector space V. Then the sum of these subspaces, quotient out by W, is isomorphic to U quotient by the intersection of U with W. So here we recall that the sum of two vector spaces is defined as a vector space in V that consists of vectors of the form U plus W, where U runs over U and W runs over W. This is similar to the definition of a direct sum, only for direct sums we also require that the intersection of these two subspaces must be trivial, so that is a zero vector. And this is a more relaxed case when these two subspaces may have a non-zero intersection. So here we have that W is a subspace inside U plus W, and the intersection of U with W is a subspace inside U. So this tells us that these quotient spaces are well defined. To prove this result, we want to construct a linear transformation T from the space U into this quotient space, U plus W, quotient by W, where T applied to a vector U will be defined as the class of a vector U. And written as a coset, this will be vector U plus the subspace W. Now, the fact that T is linear is rather obvious. This follows from the way how we define operations on equivalence classes. Now, what we want to do is we want to show that T is surjective, and we want to show that the kernel of T is precisely the intersection of U with W. To prove that T is surjective, we need to show that an arbitrary vector in this quotient space has a pre-image under T. But what is an arbitrary vector in this quotient space? So this vector will be written as a class of U plus W, because this is how vectors in the sum of these subspaces are formed. But this is equal to the class of U plus a class of W. But the vector W belongs to the subspace W, so this means that this class is equal to 0. And so what we have is we have just the class of U, but the way how T is defined, the class of U is equal to T of a vector U. And so we see that an arbitrary vector in this quotient space has a pre-image under transformation T. So from here it follows that T is surjective. Now let us compute the kernel of T. So let U be an arbitrary vector in the space U, which is the domain of our transformation T. Then what does it mean that U belongs to kernel of T? This is equivalent to saying that T applied to vector U is equal to 0. But the values of T are in the quotient space, so a 0 vector is written as the 0 class here. Now, our definition of T was that T associates to a vector U its class in the quotient space. So what we get is that the class of U is the 0 class. But if the class of a vector is a 0 class, this means that this vector belongs to the subspace that we quotient out. So this is equivalent to saying that our vector U belongs to the subspace W. And because to begin with, vector U was in the subspace U, we see that this is equivalent to saying that U is in the intersection of W with U. And now we see that U is in the kernel of T, if and only if it's in the intersection of U with W. So we get the equality of these two sets. And now let us apply first homomorphism theorem to the linear transformation T that we constructed to this one. So what we get is that U quotient by the kernel of T is isomorphic to the image of this transformation T. But we proved that T is surjective, so its image is the space U plus W quotient by W. And the kernel is the intersection of U intersection with W. And what we get is that the quotient of U by the intersection with W is isomorphic to the quotient of U plus W by W. And this result is a consequence of the first homomorphism theorem. Our second result is the following theorem. Let W be a subspace inside U, which is a subspace inside V. So be a chain of subspaces. Then the following quotient space. So we take V quotient by W and quotient this by U quotient by W. Then this is isomorphic to V quotient by U. So here, since U is a subspace in V, U quotient by W is a subspace inside V quotient by W. And so then we can form this quotient. And the claim of this theorem is that these two quotients are isomorphic. Let's give a proof of this result. Consider the canonical projection P from V to V quotient by U. So what do we know about this linear transformation? Well, we know that P is surjective, and we also know that the kernel of P is equal to U. But here we have a chain of subspaces. We have that W sits inside the kernel of P, which is U. And now we're in a situation of the second homomorphism theorem. So we have a subspace that sits in the kernel of a linear transformation. So by second homomorphism theorem, we have a linear transformation P bar from V quotient by W into V quotient by U. This transformation P hat sends the class of a vector V, which we will write as a coset V plus W, into the coset V plus U. And this tells us that this map P hat is surjective. Now let us compute the kernel of P hat. So what does it mean that the coset V plus W belongs to the kernel of P hat? This is equivalent to saying that P hat of this class, V plus W, is the zero class here, but the zero class here is U. And this is equivalent to saying that the coset V plus U is equal to U, which is equivalent to saying that vector V belongs to U. Now this tells us that the kernel of P bar is the quotient space U quotient by W. And now all we have to do is we have to apply first homomorphism theorem to P bar. The map P bar is defined between these spaces, and it is surjective. So the image of P bar is V quotient by U. And by first homomorphism theorem, we get that this image is isomorphic to the domain V quotient by W, quotient by the kernel of P bar, which is U quotient by W. And that's exactly what we had to prove in this theorem. So we see that in the proof of this isomorphism theorem, we made effective use of both the second and the first homomorphism theorems. The three homomorphism theorems that we proved today are versatile tools when working with quotient spaces.